is equal to 1 over 2 pi integral from minus infinity to plus infinity, and phi of k, this is e to the power I k x while t is equal to 0, and dk. So this is our wave function, means the time independent wave function, and from this we will now determine the value of phi of k, and as we get the value of phi of k, then we can get sine x of t. Now how to get phi of k? I can write that if I multiply this with e to the power minus ikx, then I can write that phi of k is equal to 1 over 2 pi integral from minus infinity to plus infinity, and sine of x0 e to the power minus ikx dx. In order to find this f of k, or just switch from the real space to the momentum space and from the momentum space into the real space, it is not a simple multiplication of e to the power minus ikx, but this is under the Planck theorem, and the Planck's theorem states that when f of x is equal to 1 over 2 pi square root and integral from minus infinity to plus infinity, and we are having capital F of k, then e to the power ikx, and this is in dk. As this is f of k, so we are having dk, and this thing is interconvertible, means from one into another we can go back, that f of k, now this f of k we can write is 1 over 2 pi integral from minus infinity to plus infinity, and f of x, now this f of x is actually this one, and e to the power minus ikx and dx. So this we call the Fourier transform. This is the Fourier transform. This is the Fourier transformation of f of x, means moving f of x to f of k, and this one is called the inverse Fourier transform. Fourier transform. The inverse Fourier transform of f of k, because our f of x is in the real space while f of k is in the k space. K space we deal in Fourier transform, while x space, the real space, we will deal in inverse Fourier transform. So we can find this f of x from here, like psi of x from here. If we find f of k, the phi of k, then we can determine our psi of x0 from our psi From our psi of x0 we can determine phi of k, and from phi of k we can determine psi x of t, and we can make it normalizable. Now in order to understand how the Planck's theorem is working and how we will be able to find our wave function, we want to solve an example, and this is example 2.6, and which is on page 74 of the second edition of Griffiths. And the example says that a free particle that is initially localized in the range, we are having a particle and the particle is free to move. It is initially localized between x plus a and minus a, and it is released at time t equal to 0. So psi x of t is equal to a when x is less than plus a and greater than minus a, and this particle is equal to 0. Here this is psi x of 0 because at time t equal to 0, and this is equal to 0 otherwise. So we are having a particle localized first, and here we will have to keep in mind that a and small a are actually constants, and they are positive and real, and we are supposed to find psi x of t, means what will happen to the wave function after time t. So the very first, let me solve the problem. So the solution is that the very first thing, we will have to normalize our wave function. So our wave function normalization condition is that from minus infinity to plus infinity, psi mod square dx will be equal to 1, and this implies that if I square this one, no iota is involved, so it will be the simple square, and I can write is this is a mod square, and then from minus, this is from minus infinity to plus infinity, but our particle motion, our wave function is restricted in -1 and minus a to plus a, so I will restrict my particle in this range and dx. So it will be a squared, and then dx will become x from minus a to plus a. So I can write that this is equal to a square and 2a, because a minus minus a, so a plus a and 2a is equal to 1, and this implies that a is equal to 1 over 2a. So our wave function psi x of 0 came out, to be 1 over 2a. Now we will have to compute phi of k, because our psi of x0 is now known to us. So we will compute phi of k, and phi of k we can compute from here. So I will write that phi of k is equal to 1 over 2 pi and integral, and this will be from minus infinity to plus infinity. So our limits are from minus a to plus a, because in this range our psi x of 0 is 1 over 2a, and then e to the power minus I k x dx. So this will give us the value of phi of k. Now one more two-way, I can move it out, and this will be 1 over 2 pi and 1 over 2a, and integral from minus a to plus a, and e to the power minus I kx dx. Now I know the solution of this, that this is equal to 1 over 4 and phi a, and from this will be e to the power minus I kx divided by minus I k. So let me put the limits, and we will have 1 over minus I k will be out. So I can write 1 over 2 will be out, and then minus I k and square root of pi a, and then we will have the limits in this. So we will have e minus I k a and minus, and e when x will be equal to minus a, so minus a minus a will become plus I k a. These will be the limits. So if I write them e I k a minus I k a, and I move this 2i here, so the minus will cancel and 2i will be utilized there, and I can write that phi of k is equal to 1 over k pi a, and this will become sine of k a, according to the relation that we have written earlier, the Euler formula. So this phi of k is equal to 1 over pi a and sine of k a divided by k. So whole divided by k. This is our phi of k value. So we are having the psi of x0. Psi of x0 is this one, while phi of k is equal to this. So from here we can now solve our psi x of t. So psi x of t will be equal to 1 over 2 pi. For pi of k, I will put this value, and then this will be equal to psi of xt. It will be equal 1 over 2 pi and then 1 over 2a and then 1 over pi a. So when all the constants are there and I simplify them, I will have 1 over pi times 2a, integral from minus infinity to plus infinity, sine of ka divided by k, and e to the power I kx minus h bar k square over 2m and t. So this will be the h bar k square in 2m over t. So we will have a dk with it. So if we solve this integral, then we will get psi x of t. Although the integral is very difficult and it can be solved on with the help of numerical solution. So we will leave the integral at this place, considering it to be the solution of our psi x of t, means our wave function will evolve like this. But we will discuss a little bit these two solutions here, and we will discuss them with the help of limiting cases. So, limiting cases. So the limiting conditions are that, let's say I am having on one axis, let's say this is y-axis and this is x-axis, and on this side I am having x, while here I am having x and 0. Now our wave function psi of x0, I know that it is 1 over 2a. So if I apply a condition, and a condition, the limiting case is that if a is very small, then if a is very small, then it means my wave function is restricted in a very small space. So for a very small space, I can now plot this one, that let's say this is minus a and this value is plus a. So my wave function is limited in a very small range, and I will say that it is very sharply peaked like this, and this top value is actually 1 over 2a. Now I know the uncertainty principle, the Heisenberg uncertainty principle, that when I will restrict the space, then the reciprocal space will be too large, or I know that delta x and delta p, if I restrict this one in a very small space, then delta p, the uncertainty in momentum, momentum is h bar k, k space we are plotting, so this will become very huge. And let's see that what will happen if I plot here the k here, then here I will have phi of k. Now when this is very sharp, then what will happen to phi of k here? As I know, phi of k is equal to 1 over pi a and sine of ka divided by k. So if a is very small, then I know that sine theta is approximately theta for theta very small. So this sine Ka will actually approximate to Ka, and I will write that phi of k is approximately equal 1 over pi a, and this will become Ka divided by k. Now k will cancel, and this a will simplify with this a, and this will be then equal to a over pi and whole square root, because I can write this square root a, one will simplify. So phi of k is approximately a over pi, and what will happen that this will be too broad, or the end limits will be just like this, and this will be the value of phi of k. So if I restrict space, the momentum become huge, and when I restrict the wave function in space, it will be not restricted, or it will be huge, extending to minus infinity to